like I said, chapter kind of takes a turn here, and we look at rational functions. One of the biggest concepts of rational functions is where are the asymptotes. So we're going to get to, when we get to calculus, you are going to be asked to call upon your knowledge of what a quick sketch of a graph looks like a lot. So last year you weren't tied to this because you always had a calculator. You could just plug it in. But when you don't have a calculator in calculus and you're asked about the slope of something at a certain point, or whether or not it's continuous, you're going to need to be able to sketch graphs. And so we kind of are going to review this idea here. Rational functions always have two asymptotes. They can have more, but at least two. So here's our parent graph. We have a vertical asymptote at x equals 0. That's our vertical one. Now, vertical asymptotes always come from the denominators zeros. Denominators zeros. So we could write a rational function, and we'll see some today, that have multiple zeros in the denominator, and therefore they will have multiple vertical asymptotes. But for the parent graph, we just have the one. And then your horizontal asymptote comes from the fact, like, take a look at your parent graph. This is when y equals 0, right? Do we all agree? That's y equals 0. Explain to me why this will never equal 0. Why will 1 over x never equal 0? Liam. Very good. The 1 in the numerator is constant, and in order for a fraction to equal 0, the what needs to equal 0? The numerator. In order for a fraction to ever equal 0, the numerator needs to equal 0, and that will never happen because the 1 is glued in there. Yes? So we get a horizontal asymptote at y equals 0 in our parent graph. And therefore, because we have vertical asymptotes, our domain is limited. X can be any real number, except it cannot equal 0. Vertical asymptotes limit your domain. Horizontal asymptotes limit your range. Y can be any real number, except 0. What's that? Not always. You have y's that are greater than 0, but you also have y's that are less than 0. So it's all real numbers except for 0. Does that answer your question? Okay. And then our end behavior of rational graphs we'll talk about a lot. This is a notation that we're going to get more and more into, but normally you would say as x approaches 0. Does anybody know what this little superscript of a plus sign means? Not to the right, really kind of from the right. As x approaches 0 from the right-hand side. So here's 0. As my x values are approaching 0 from the right-hand side, what's happening to my y values? They're increasing towards infinity. But it's different if I'm approaching 0 from the left-hand side. As x approaches 0 from the left-hand side, see how my x coordinates are getting closer and closer to 0? But coming from the left-hand side, what are my y coordinates doing? Stephen? Very good. Okay? So, up until this point, you've probably mostly only talked about what happens to graphs as x approaches infinity or as x approaches negative infinity, end behavior type stuff, right? But now we have to look at what happens to a graph as you approach an asymptote. And anytime you approach a vertical asymptote, your graph is either going to shoot up towards infinity or shoot down towards negative infinity. When you approach a vertical asymptote, your graph always kind of flies off the handle towards infinity or negative infinity. Does this make sense? Okay. We still will talk about end behavior. As x's approach infinity, what is the y coordinate approaching? 0. Very good. It's getting closer and closer to 0. It's getting closer and closer to that horizontal asymptote without ever actually reaching it. Think about that. If you plugged in 100, your y value is 1 over 100. That's a pretty small number. If you plugged in 1,000,000, your y coordinate would be 1 over 1,000,000, which is an even smaller number. Not 0 yet, but getting closer and closer to 0 as x gets bigger and bigger. Does this make sense? Okay? And then as x is approaching negative infinity, so here my x coordinates are getting smaller and smaller and smaller, approaching negative infinity. What are my y coordinates getting closer and closer to without ever reaching? 0 as well. Good. So we'll talk about approaching infinities and behavior like we always have. And here's the other thing with rational graphs, just to kind of summarize. As you approach infinity and negative infinity, your y function is generally, not always, but most of the time, going to approach that horizontal asymptote. As you head up towards infinity, you're usually approaching that horizontal asymptote. Does this make sense? Okay. So let's take a peek at these graphs down here. And at the top, I just talk about if a is a 0 of q of x, so your zeros of your denominator, it's a vertical asymptote. So we can actually say then x equals a is a vertical. We can be more specific about that asymptote, as long as a is not also a 0 of p of x. I'll elaborate on that second part of that sentence in a minute. But for the time being, in our first example, we have f of x equals x over x squared minus 9, which we'll factor. I didn't mean to rewrite that. Why don't we write the original problem again? X squared minus 9 factors into x plus 3 and x minus 3. And so from our denominator, we have two excluded values, is really the way you talked about this last year. Your excluded values, so your domain, is that x can be any real number, except x cannot equal what two numbers? -3 and 3. So that's my domain. And therefore, my vertical asymptotes are those numbers. X vertical asymptotes are at x equals 3 and x equals -3. And I'm going to how about horizontal asymptotes? Are there any numbers that y cannot equal? I don't think so. We're going to get more into horizontal asymptotes in a minute. There's some rules that you have to know. But x divided by x squared minus 9. And you'll see what this graph looks like. And you see your vertical asymptotes? Yes? Okay. You have two of them. You don't, it looks like we have a horizontal asymptote at 0, doesn't it? Here's one key difference that you may not know about asymptotes. Vertical asymptotes cannot be crossed. They're undefined points on a graph. Horizontal asymptotes can be crossed. So this central part of the graph is crossing, and we do achieve a value of y equals 0. But this line y equals 0 is still an asymptote because when you're moving towards end behavior, this portion of the graph is getting closer and closer to it without crossing it. And this end of the graph is getting closer and closer to it without crossing it. So horizontal asymptotes really serve as a guide for your end behavior. Your graph is allowed to cross horizontal asymptotes as it does here. That's a key point. Does that make sense? All right, we'll look more into that in a minute. This next graph, if I simplify it and factor my denominator again. What do you notice about how this can be simplified? What does this simplify to? 1 over x minus 3. Okay? So here's a key fact. This x plus 3 cancel. Okay? Our only asymptote is at x equals 3. But our domain is still has to exclude both of these values, plus or minus 3. Okay? So our domain is that x is all real numbers, but x cannot equal negative 3 or 3 again. That's still our domain. This one, pay attention here, because it still is undefined even in the most simplified version. If it's still undefined at x equals 3 in the most simplified version, this is still a vertical asymptote, x equals 3. This one, however, is not a vertical asymptote. This is going to produce something called a hole at x equals negative 3. So they're both undefined points on the graph, but this one, because it canceled out, creates a hole, and this one creates a vertical asymptote. So let me show you how that's going to work. So if I plug this new function in, now you have to know about the hole because your calculator is not going to show it very well. Okay? So we see our vertical asymptote still at x equals 3. Yes? Okay? We know this function is undefined at negative 3, because if I plug in a negative 3, I'm going to get 0 over 0, right? So it's still undefined at negative 3 over here, but you're not going to see an asymptote there, because that asymptote kind of worked itself out in the simplifying process. It got simplified out. So it's not an asymptote. It's instead a hole. For example, if I go to trace and I find the, not 0, second trace, and I look for value, and I want to find the value of this graph at x equals negative 3, it's going to come up blank because there's a hole there. So if I were doing this by hand, I would make a very obvious hole there. This graph is going to come up to that point, there's going to be a hole there, and it's going to go out of that point. And if you zoom in to that section of the graph, where's my cursor? Negative 3.1. Still not showing it. If I zoom in again, will it show it? No. I think it's a pixel reason. Sometimes our graphs will show it, and sometimes they won't. This one is definitely not showing it. I'm just really going to try to zoom in a whole bunch. That didn't work either. Sometimes the calculator shows it, sometimes it doesn't, and I don't have any rhyme or reason answer other than like the lack of quality of the screen that we're dealing with. But here's a key point. The graph of our function and the graph of this simplified version look to the naked eye exactly the same, with the exception of the actual function we graph will have a hole at that negative 3 value, whereas this function, if you graphed it via this way, would not have a hole. This equation has no reason to have a hole at negative 3. But with the exception of that hole, the original function and the simplified function are going to look exactly the same. So we'll often simplify it so that we're better able to graph this by hand, and then we just have to know that this thing that canceled is a hole at negative 3, which at negative 3, 1 over negative 3 minus 3 would be at negative 1/6. There's a hole at negative 3, negative 1/6. Okay, so you will be asked to find the points at that hole. And you can't plug negative 3 into the original to get that point because it's going to give you 0 over 0. You plug it into the simplified version, and you see that that whole is at -3, -1/6. So to do a quick sketch, we have an asymptote at 3. That's going to look like that. And we're going to have a hole. So we're going to do this. We have a hole at -3, -1/6. There's our hole. Does this make sense? Stephen? It's just a break in it. I'm putting a little very obviously open hole there, so you know that the graph approaches and gets infinitely close to the point -3, -1/6 on either side, but it doesn't actually reach that point. Okay? And this is the graph of g of x, our original function. So in summary, something that cancels creates a hole. Something that still leaves a factor in your denominator is still a vertical asymptote. Any other questions on that? Okay. And then this last one, the denominator is not factorable, is it? Sum of perfect squares. There are no vertical asymptotes here because no number that I plug into the denominator is ever going to make that equal to 0. So this one has no domain limitations and no vertical asymptotes. If I show you this graph, just so we can start to get a feel for things. This we would have to sketch just by kind of playing around with a table of values. Plug in an x of 0, get a coordinate. Plug in an x of 1, an x of -1, and we would get a feel for what this looks like via a table of values, which is not super efficient, but it's really the only way. So that's what I see when I plug this in. Did I plug that in right? Yeah. Okay. The graph never gets above 1, does it? Okay? The reason for that is think about any x value you plug in. If you plug in 0, you're going to get 3/9. If you plug in 1, you're going to get 4/10. If you plug in 2, you're going to get 5/13. Right? If you plug in 3, you're going to get 6/18. See, your y coordinates are continuing to get smaller and smaller, aren't they? Right? Your numerators are only jumping by 1. Your denominators are growing faster and faster and faster. So by the time we plug in 100, we're going to get 103 over, what's 100 squared? 10,000? 10,009? So that's getting even smaller than 6/18. 6/18, all things considered, really isn't that small. It's a third. But these numbers are getting closer and closer to what's happening to your y coordinates. This is 0.3 repeating. This is 0.4. This is something. This is 0.3. This is really close to 0, right? So we're getting closer and closer to 0. If I zoom in on this, is this what I want to do? And I actually would probably want to see further in that direction. So I'm going to maybe make my y max, I don't know, 20. Oh, not y. I meant my x. Sorry. See, it goes up, but then it's going to come down, and it's essentially what's an asymptote here? The x-axis, right? It's getting closer and closer. Okay. Horizontal asymptotes. This is how are we going to know where they are? Okay, essentially. So there's 3 rules that we have to know, and the rules are based on the degree of the numerator as it compares degree of numerator versus the degree, whoops, sorry, you can't see it, of denominator. Okay? And your analysis of how these two things relate to each other is going to tell you where the horizontal asymptotes are. Okay? there's three scenarios. The numerator's degree can be smaller than the denominator's. So I would say small over big. So a degree in the numerator of 1 versus a degree in the denominator of 5, something like that. There's the potential that the numerator will actually have a bigger degree than the denominator. And there's the potential that the degree of the numerator can be the same. So same over same. So after evaluating which category it falls into, it will tell us our horizontal asymptotes. If it's small over big, you just have a horizontal asymptote at y equals 0. If it's big over small, there is no horizontal asymptote. And if it's same over same, your horizontal asymptote is going to come from the coefficient or the leading coefficient of your numerator over your leading coefficient of your denominator. And you'll have to see that a concrete example of that to probably make sense of that. But you get it from the ratio of your leading coefficients. Okay? So, take a look at this first example. Kendall, what's the degree of my numerator? 1. And what's the degree of my denominator? 2. So what category would that fall into? Right, small over big, y equals 0. So your horizontal asymptote is y equals 0. And I'm going to show you that graph. Any vertical asymptotes on this one? Any place where the denominator will equal 0? No. Oops, I should hit zoom 6. Zoom 6. Okay, that's the graph of that. So you see, can you see the horizontal asymptote y equals 0 as we head towards infinity? It's going to trace along that. Yes? As we head towards negative infinity, it's going to trace along that horizontal asymptote. Good? Second one. Liz, what's the degree of our numerator? 2. What's the degree of our denominator? So this falls in the same over same, right? So here's the horizontal asymptote. It comes from your leading coefficients divided by each other. So 4 over 2, which is 2. So I'll show you that graph. 4x squared divided by 2x squared plus 1. So there's that graph. Do you see how it's headed off towards infinity? How it kind of flatlines? Yes? That's because it's flatlining along the horizontal asymptote y equals 2. That's because this one is flatlining along the horizontal asymptote y equals 2. Again, here we have no vertical asymptotes because look at your denominator. That will never equal 0. So we didn't have any vertical asymptotes. But we do have horizontal. Does this make sense? Okay? And the last one, we have big over small. Degree of 3 over degree of 2. So there are no horizontal asymptotes. So then, what happens as we approach infinity and negative infinity? So if I do 4x to the third and divide that by our 2x squared plus 1, and we take a look at this graph, okay, our end behavior is not flatlining along any horizontal asymptote. So we don't have one. Instead, our end behavior is sort of more like polynomial-ish, like where our end behavior will actually go towards infinity or negative infinity if you don't have a horizontal asymptote. Does this make sense? Yes. Like why these rules work. There definitely is. I mean, it's not just like a coincidence. There's absolutely some deeper math behind it. But I say this, at some point, geniuses figure this out by years and years and years of studying. And then when they tell us, like, this is fact, like, this is what's always going to happen, sometimes we just say thank you and we use it to our benefit. We're never going to understand completely and fully why all the time, unfortunately. Yes. I mean, don't you just accept that the three angles of a triangle add up to 180 degrees? Do you know why? There are some things we just accept. Now, I could prove to you why three angles of a triangle add up to 180, and I could make you understand why. But again, at some point we get to a state where these geniuses, these mathematicians, figured this stuff out, and we just take it as fact.